Great. Well, welcome everybody. My name's Andrew Norton. It's great to see you here tonight, and hopefully there are a lot of people online as well. I know a lot of people signed up for this online. This evening's talk is in memory of our colleague, Simon Clarke. Simon was a member of the astronomy group here at the OU since 2005, until he sadly passed away in 2021. Simon was a world leader, and he really was a world leader in research into massive stars. And he was also an excellent teacher of astronomy and astrophysics on our OU courses too. This evening, delighted to be joined by some members of Simon's family. It's great that you were able to be here. Today, earlier in the day, we've had a science meeting with many of Simon's research colleagues from around the country and indeed around the world, and delighted that many of them can join this evening's event as well. So, this evening's speaker is Professor Simon Goodwin from the University of Sheffield. Simon and Simon Clarke worked very closely together on a number of research projects over the years, and this evening Simon is going to reflect on their work and the field of massive stars in general. So, please welcome Professor Simon Goodwin to talk about the rock and roll stars of astronomy. Simon.
Great, thank you. It's a great honour to be giving this talk. I wish I wasn't, but it's nice, if you know what I mean, to be able to do it and to talk about some of what Simon Clarke did and what we all did together. We've had a research meeting today, as was just mentioned, where we've been doing all the nitty-gritty bits of science that you tend to get spend all your time doing. We've been looking at lots of squiggly lines with arrows pointing at them, and that's what you do. But for a talk like this, what I wanted to do more was talk about the bigger picture, which often when you're doing something, you sort of forget about why it is we're doing this, what it is we're trying to learn, and also how you go about doing science. And the way we go about doing science isn't often the way that even we as scientists portray it. It's a lot more messy and it's a lot more fun. I'll carry on talking. So the reason that I think you do science, and especially you do astronomy, is you want to know why the universe is like it is, how it is things work, and why it is, and there's a lovely picture of the night sky. So yeah, what we're wanting to do, and what Simon and all of us wanting to try and find out, is why the universe is like it is. What will come up is a lovely picture of the night sky. Because as astronomers, what we want to do is look out at the universe. And when you look up at the night sky, often here you don't get particularly good views of things. But when you go somewhere dark, even in Britain, you can go out somewhere dark and you get a lovely view. You see all these stars. And we've got a fairly good picture we've put together of how we think the universe has appeared and why it's like it is. And it starts at the Big Bang, about 14 billion years ago, where the universe appeared from nothing. Laura knows more about cosmology than I do. And then when it started, it was a pretty smooth mixture of just basically hydrogen and helium. And when you look at the universe now, it is very different. And in particular, we're standing on a planet which is largely made of iron, silicon, oxygen, magnesium, and things that weren't created in the Big Bang. We are living things, and all the living things are made of carbon, oxygen, and nitrogen, which weren't made in the Big Bang. And so when you're looking around at all these interesting objects in the sky, you're looking at stars, you've got planets around them, you've got life on at least one of those planets, and all of that is made up of things which weren't there originally and so have been created. So there's a classic quote from Carl Sagan about "we are stardust," that the stuff that makes us up has been made inside stars. And so understanding this where the chemical elements have come from, why it is the universe looks like it does, how it is we can have a universe that we exist in, really important part of that question is looking at massive stars, because massive stars are the place where you make an awful lot of the stuff that makes up planets and makes up life. And they also control how galaxies like our Milky Way look like they do. They regulate the amount of star formation that goes on. And we're not quite there yet. I'll keep blocking. And so in wanting to look at massive stars, and the thing that sort of drives us fundamentally when we're trying to look at these things is trying to understand where these very rare but really, really important stars come from. How do you form these things in the first place? How do they evolve? And then after a few million years, they will explode as supernovae. They'll distribute elements through the universe. We there? Yay! Thank you. So that was the lovely picture that I was having. I said the Milky Way and the vast numbers of stars in the Milky Way. I'm trying to understand why it is when you look at the night sky, how we can stand on a planet like the Earth and look out, and why is it like this? So the star we know the best is the Sun. This is a pretty bog standard star. So our Sun is a bit heavier than average, but not very much. It's sort of fairly standard. It's currently about 4.5 billion years through its life cycle. It's an interesting thing about an astronomer, that we bandy around stupidly big numbers all the time. So to an astronomer, it's 4.5 billion years. And we go, oh yeah, that's quite old. To anyone else, only a geologist, I think, deals in these sorts of huge, silly numbers like we do. So Sun's about 4.5 billion years old, and it's been sat around for about 4.5 billion years, not really doing very much. Now, this in terms of the Sun, and in particular the Earth and life on the Earth, is great. The Sun's got a little bit more luminous over 4.5 billion years, but generally speaking, it's not done much, which is good because it's allowed life on the Earth to form probably about 3.5, 4 billion years ago, and then it's evolved, and now we are here with sort of an intelligent technological civilization that's capable of building the pyramids or Angkor Wat or designing the centre of Milton Keynes and other amazing achievements such as that. And it's going to carry on doing this for about another 5 billion years or so. We're about halfway through its main bit of its life. What it's doing at the moment is, in its core, it's burning hydrogen into helium. You take 4 hydrogens, you bung them together, you get helium. That releases energy, that powers the Sun, that keeps us warm. And it's going to keep doing that. Things get slightly interesting with the Sun in about 5-ish billion years' time, where it runs out of hydrogen in its core, and then it's got helium, and it can start putting that helium together, and it can make carbon, and it can make oxygen, makes a little bit of nitrogen as well, and it swells up, and it becomes what's called red giant. This is the point it will eat the Earth. So, well, actually, as it gets gradually warmer, life on Earth will stop in about 8 billion years. The Earth will become uninhabitable. So we've got about another 3.5 to worry about that. So we're probably okay. And then about 10 billion years old, it will eat the Earth. Then it sheds its outer layers and it becomes what we call a white dwarf, which is something about the size of the Earth, made of carbon and oxygen. And that just really sits there and doesn't do very much. And this is what most stars do. And if the universe was made up entirely of stars like this, we wouldn't be here. Because all these stars do is at the end of their lives, they'll put out a little bit of carbon and oxygen and nitrogen, but not very much at all. And so this will be a very, very boring universe to live in. And in fact, we couldn't live in it because you wouldn't have planets and you wouldn't have life. So this is what most stars do. And it's interesting enough. I mean, this we understand relatively well. What's much, much more interesting, though, are massive stars. So this is to scale. Most stars are actually smaller than the sun. Most stars are red dwarfs, so tiny, tiny, tiny little things. The sun's a little bit bigger than average. Things like red dwarfs and stars like the sun make up 98%-ish of all stars. So when you look out, it's most, well, actually, those things are so faint you don't see them. There's quite a few of those around. We're interested in those because that's like our sun. We know they can have planets around them that have life because we're here. So there's quite a lot of interest in those. What we're particularly interested in is these much bigger things. So blue dwarfs, and behind this is Paul's Monstar R136a, which are really, really massive stars. So these are somewhere between about 10 and probably 300, maybe a bit more times the mass of the sun. They're much, much, much bigger than the sun. Because they're much bigger than the sun, they've got a lot more gravity. Their central temperatures and pressures are a lot higher, so they burn through their hydrogen fuel much, much faster. These things, whilst they're rare, they're only about 1-ish% of all stars. They're burning through their hydrogen fuel at about 100,000 times the rate of the sun, which means they're 100,000 times brighter. So whilst they're very rare, they are incredibly bright, which is great. They're really easy to see. And these are really interesting because these are the places where you get beyond carbon, hydrogen, and carbon, oxygen, and nitrogen. So they burn through the hydrogen really quickly in only a few million years. Now, to an astronomer, only a few million years, that's really quick. So they're burning through their hydrogen in no time at all. They're turning that into helium. Then they're big and massive enough, they can take the helium and they can start fusing that into carbon and oxygen. Then you can start fusing that and you can make things like magnesium and neon and silicon and sulfur. So you can build up quite a lot of heavy elements. And a lot of these elements are the things that life and planets are made of. Life made mostly of carbon, oxygen, nitrogen, and hydrogen. The Earth, there's a lot of magnesium, a lot of oxygen, a lot of silicon. And also, right in their hearts, they can burn their way up to iron. And so they can keep putting nuclei together, keep putting atoms together to build bigger and bigger and bigger things. They do this really quite quickly. So over the course of just a few million years, they're going through these phases of burning these heavier and heavier elements. All of these are giving out energy, and so these things are shining incredibly brightly. Iron, the reason this is down as iron ash is that you can make energy through fusion, through throwing two atoms together until you get to iron. As soon as you get to iron, you don't make any more energy. And so these stars, when they get to iron, they've got this iron core, they can't make any more energy, and then they're in trouble. Now, one of the things that Simon and all of us are interested in is while they're doing these late stages of their evolution, they're burning all these heavy elements, they do all sorts of weird things. All sorts of weird things that we don't really understand. So you can have things in the heart of this, there's something called a Wolf-Rayet star, it's blown off huge amounts of material. So it's all its outer layers, it's blown off. It can blow these things off at hundreds or thousands of kilometers a second. It can blow off several times the mass of the sun in sometimes a few 100,000 years. And it blasts this out. You can go through huge explosions. This is something called Eta Carinae, which for a brief period in the late 1800s became the brightest star in the sky when it went through a huge eruption. And so what we see here in what's called the Homunculus Nebula is the two shrouds of gas that it just blew off. And so as they're evolving, they're producing so much energy, they're not very stable. And so they're throwing out lots of material and going through all these strange stages. And then, very important thing they do right at the end of their lives is once they've burnt up to iron, I was about to say you can't burn iron. You can fuse iron, but the trouble is it doesn't give you any energy. It actually takes energy away. So in the heart of these massive stars, you get this core of iron, which can be a few times the mass of the sun, and it's no longer producing energy. So it collapses in the course of a few seconds. So you've got this enormous great thing made purely of iron, and over the course of a few seconds, it collapses down. Collapses down to something about 10 kilometers across. And that releases a huge amount of energy. And this is what we call a supernovae. So you get this collapse, it releases an enormous amount of energy, and it just blasts off the outer layers of the star. For a lot of a massive star's life, it's something like 100,000, maybe a few 100,000 times brighter than the sun. One of these explosions, it can be many millions of times brighter than the sun. You can have as much light produced by one supernova explosion as all the other stars in the galaxy put together. You don't want to be too close to one of these. If you're within about 100 light years or so, then as the shockwave of this hits you, you've got a lot of gamma radiation released from this. You've got a lot of material. It's traveling at sometimes tens of thousands of kilometers per second. Lots of high energy particles. It will do nasty things to your planet. Some of these have gone off relatively nearby. So fairly recently, we see evidence of some of those shockwaves from supernovae hitting the Earth. When you look in deep sea sediments, you see layers with material in them that you go, this is very weird. And so the last one that went off relatively recently was probably about 10 million years ago. And interesting aside on this, there was a megafauna mass extinction event a few tens of thousands of years ago where lots of very, very, very big animals went extinct. Small ones weren't affected at all. And some people have put that down to a nearby supernovae, where a blast of gamma rays came through, and the bigger you are as an animal, the more gamma rays you're going to get. And so potentially we lost all these enormous animals, the megafauna, because of a nearby supernovae. And we know you get these nearby every couple of million years or so. But thankfully one's not going to go off nearby soon. Thing that's most likely to go supernovae nearby is probably Betelgeuse. So in Orion, you've got the belt, you've got 2 stars of the shoulder. The really red one there is a massive star. It's in the late stages of its evolution, and it's doing all sorts of weird stuff at the moment. It will almost certainly go supernovae. It might be tomorrow, it might be in a million years. It's far enough away that hopefully it's tomorrow, because it would be really spectacular in the night sky. Last time we had really nearby supernovae go off was 1600s, and it was actually visible in the day, because these things are so bright. So for a few weeks, you could see it in daylight. So these are really spectacular explosions. Release a huge amount of energy, and importantly, release a lot of these very heavy elements as well. At the end of this, the core of the star, which collapsed down, it might leave you what's called a neutron star. So this is something 2 or 3 times the mass of the sun that's 10 kilometers across. That's phenomenal density. The escape velocity from that is something like 1/3 the speed of light. And we see these things. Or it could leave you a black hole. If it's more than about 3 times the mass of the sun, then nothing's going to stop that collapsing, and you're going to end up with a black hole. So what these things leave behind are these incredible extreme objects as well. But possibly the most interesting thing they do is they release all these chemical elements. So all these heavy chemical elements, the ones that make the Earth and us up, are all released in one of these things. So this takes me back to the sort of quote from Carl Sagan about we're literally made of stardust. So these make a lot of the heavy elements, and they're sort of responsible for really heavy elements. If you get a neutron star, or rather if you get a massive star binary, so you've got 2 massive stars and it leaves you 2 neutron stars, then those 2 neutron stars can merge. And when those 2 neutron stars merge, they explode as different type of supernovae. And they make the really, really heavy elements. So if anybody's wearing any gold, that was made in a neutron star merger event, which I always like that. So I'm not a fan of gold, but it's sort of, ooh, just, the only way you can make things that heavy is in these really extreme events, which again require you to have these massive stars. And the force of this explosion throws stuff out, and it changes the way the galaxy looks. It blows away any gas that's forming, can stop stars forming, it can cause stars to form. So the next generations of stars form from the stuff left over from these massive stars. So what we'd like to do is really try and understand what these things are doing. Trouble is, we think we understand the broad outline. So what I've given you is just sort of, yeah, that's the sort of basic idea of what these things do, and I've swept a lot of stuff that we've been talking about today completely under the carpet, because there's an awful lot we don't understand. So, phrase I know Simon appreciated, that we're going to have to science the shit out of this. Where science gets really interesting, I think, is when you really don't understand what's going on, and when you're trying to put pieces of evidence together and try and work out what's happening. So when we approach this, we're going, these massive stars, they're really important. We want to know what's going on. So how do we do this? Astronomy is, for one of the, what are usually called the hard sciences, really quite unusual. When you're in a physics department, everyone else has got labs, and they can do experiments. When you're in astronomy, you can't do that. We're dealing with utterly ridiculous extreme things, conditions that you couldn't possibly replicate in a lab. And so what we're stuck with is observing. So all we can really do is you build yourself telescopes. So this is the VLT in Chile, and you look and you see what you see. And then you try and understand what it is that you're seeing. And sometimes it's easy, and sometimes it's not. And telescopes and observing are sort of really the heart of this, and Simon was an observer, which meant he used telescopes a lot. Now, one thing about where telescopes are, this is a map, the red dots are sort of where a lot of the telescopes are. Big yellow dots are sort of three of the main places where you can go observing. So, well, I put this one down because I've got a story about that. There's Australia, that's quite good. Chile is a really good place to go observing. Hawaii, great place to go observing. One thing you'll notice about these is they're a long way from us. So astronomy involves a lot of long-haul flying. I have never met somebody who hated flying as much as Simon. Astronomy was really not a good career choice for somebody who hated flying that much. Regularly going out to Hawaii, I flew with him to Australia, which was an experience. Because for some reason, all I can think is it was probably for the air miles. We went to Australia the long way round via the US. So it's a really long haul flight. It's all the way to LA on the first leg, then flying out to Australia across the Pacific. And he hated every minute of it. And he did these sorts of things regularly. Now, one thing you want to do with building a telescope is you do want to put it a long way from civilization. Because with civilization, you get streetlights. And they go shine up, and we get what you call light pollution. You also get air pollution. So you get dust in the atmosphere and smog, all of which gets in the way of your observing. You'd like ideally to be up a mountain. You want to be as high as possible, because that gets you above a lot of the atmosphere. And you want to be somewhere really dry if possible, because water vapor in the atmosphere is really annoying if you're trying to do any observations. So somewhere up a mountain, away from civilization, and somewhere dry. And one thing you'll notice about these, this is the southern hemisphere of the equator, because due to oddities of how the sun is going around the galaxy and how the Earth goes around the sun. If you're in the northern hemisphere, we get the boring half. Our sky is actually remarkably boring. Anybody who's sort of been down to the southern hemisphere, especially somewhere like Australia, knows if you look up in the sky there, it's way, way, way more interesting. Most of the interesting stuff in the galaxy is that way. So you want to put things in the southern hemisphere or maybe on the equator. If you're on the equator, you can see both sides. But putting stuff in the northern hemisphere is not ideal. And especially since most of the galaxy's in that direction, that's actually where most of the interesting stuff is. So where the center of the galaxy is, which we've had a number of talks about today, lots of massive stars there. There's a cluster I'll talk about, Westland 1, that's that way as well. There's large and small Magellanic Clouds, which are really interesting. They're both that way. So the northern sky is really boring. So you want to go to the south. Now, something most astronomers moan about, Simon moaned about to me a lot, is as an astronomer, you say things to people like, oh, I've got to go to Hawaii next week. And the reaction you normally get is, oh, poor you. And it's sort of, well, yeah, actually. Because when you say Hawaii to people, that's your picture. You've got beaches and you've got palm trees and it's lovely. And in the background, to make it look even prettier, you've got this lovely mountain. Trouble is, when you go observing, that's where you go. You don't really get to see much of the down at the bottom bit. And also, you've just flown halfway around the world. So you're jet lagged, and then you've got to go up a mountain and work nights. It's really not as interesting as it sounds. If you're lucky, you can get a couple of days holiday, but largely you need that to recover from the flight and the working nights. Because where you end up going is something like the top of Mauna Kea in Hawaii, which is about 4,000 meters. That is not a nice altitude to work at. You're really lacking in oxygen. One of the most disappointing things about going up that high, I found, was you think, well, I'm at 4,000 meters. The reason they picked this place is because it's a brilliant place from which you can observe the sky. So surely I am going to have some amazing views of the night sky. No. If you're at 4,000 meters, the amount of oxygen is so low, your brain starts shutting down certain functions, and your eyesight gets a lot worse. You lose a lot of your color vision, and you lose a lot of your peripheral vision. So actually, it's a rubbish place to go outside and look at the sky from. Brilliant place to build a telescope, but, oh, yeah, working nights at 4,000 meters, not a particularly pleasant experience. I mean, you get some amazing sort of data from somewhere like this, but it's not as exotic as it sounds. Now, I'm a theorist. Pretty much everybody here is at the meeting today is an observer, which means they're the ones who actually go out to the telescopes. I've never really fancied doing that. Flying halfway around the world to work nights at altitudes does not fill me with joy. I like computers and I like working normal hours. But I have been observing twice, and both of these were thanks to Simon. So I did get the chance to see this place, which is the Atacama Desert in Chile. This is an absolutely amazing observing site, and it's where the very large telescope, the VLT, is currently based. They are also building there the ELT, the extremely large telescope, which hopefully will be operational in 2 or 3 years, and that is going to be amazing. These are somewhere towards the big end of telescopes, so they're about 8 meters in diameter, which is sort of one side of this stage to the other. And that's impressively big. When you see a mirror that big in real life, you sort of go, wow. The extremely large telescope will be 40 meters. It's going to be absolutely enormous. And they're building it in the middle of the Atacama Desert because this is a great place to be if you want to observe. It's dry as a bone. It's one of the driest places on Earth, which is why it's brilliant to put telescopes there. It's about 2,500 meters up, which is pretty good. There's other places in the Atacama that go up to 5,000 meters, so fantastically good places to put certain instruments. But oh, is it dry? It's so dry. Humidity's 10, 20%, which means you are permanently thirsty. It's difficult to get to. It's not the sort of place you would go as a tourist. So it was fantastic to be able to go out there. It was complete luck, because Simon was extremely good at writing telescope proposals. So this is where you try and persuade the people who run this to give you some time on their massive, expensive instrument. So you've got to write an argument where you go, oh, we want to look at these things because they're really, really interesting. Simon was very good at writing those and put together a proposal to go observing. And there were lots of people on it, and I was on it as well, because I wrote some stuff about what we'd do with the data once we got it. Never thought I'd actually go there. And I got a phone call from Simon going, do you want to go to Chile? I was sort of, yeah, go on. And he went, because I've gone through everybody on this proposal, nobody else can go. So I've got to the point that I'm going to have to ask you. So he came up, he gave me a quick crash course in observing, and then I went off to Chile, and I went out, and it was great. And it was really exciting, because I don't think they're used to theorists going out there. So I got a tour around the telescopes, because I was just looking around and going, oh, this is amazing. They said, so I'm not used to people being this excited by this. They're normally bored of this. And I did get to go to the Atacama, which is a spectacular place. You can also go other places observing. My first observing trip with Simon was, he emailed me going, fancy going to Australia? I went, yeah, all right. He got some time on a radio telescope. This is ACCA in Australia. Great thing about radio telescopes is you can use them during the day. So if the object you're interested in looking in is above the horizon, you don't actually care whether the sun's up or down. As radio waves come, they don't care whether the sun's there at all. The sun isn't that bright in the radio. So he got about 3 days where every day was 20 hours solid observing. So not something he could do himself. And he said, well, it's not too difficult. Generally speaking, you just have to type stop and start. I think even you can cope with that. So I went, yeah, all right. So we went out, and this was the one where we went the long way round. The worst bit of this actually was the last leg, because this is in a place called Narrabri, which is in the middle of nowhere. I've never met anybody, apart from an astronomer, who knows where it is. It's a tiny little sort of farming town, middle of nowhere in Australia, and it's got these radio telescopes there. And the last leg was a flight from Sydney up to Narrabri in a really small plane. And thankfully, Simon was very happy to give me the window seat, because I could look out and see. It's really interesting. That he hated more than the other flights we did in this small, rickety plane. And we got there. Australia is famous for being full of dangerous creatures. When we first walked into the telescope control room, there was a small fridge with a big red cross on it. And above it was a map showing you the locations of the 10 deadliest snakes in the world, all of which live in Australia. 8 of these overlapped in one tiny, tiny little place. I was looking at this, and the guy came up behind me who worked there and went, guess where we are? And I said, it's there, isn't it? And he went, yeah. And he said, but I've been here 10 years and I've never seen any of these. So you don't have to worry about snakes. Things you have to worry about are dunny spiders. So he said, you want to flush the loo before you sit on it, because there's a type of spider that will sit underneath the toilet seat. When you sit on it, it will jump out and bite you. He said, it's highly unlikely to kill you, but you won't be able to sit down for a month. So it's sort of, okay. But then he told us about the most dangerous thing around at the time, which was one of these. So we turned up during wallaby mating season. And ATCA, being a series of big radio telescopes that you can move around, is on a big open plain. When I arrived there, there were wallabies everywhere. There's just little cute things bouncing around. I thought, oh, that's really cute. This is amazing. Wallabies everywhere. In mating season, this is a male wallaby. I looked through various pictures. During mating season, apparently they get very aggressive. And they can smack you with their back legs and shatter your legs. Kangaroos can kill you because they're bigger, so when they decide to kick you, they tend to kick you in the chest. Wallabies apparently will just break your legs. And they'll do it for no apparent reason because it's mating season and they're getting all aggressive. So this was not the animal I thought I was going to have to be most careful of, but there were loads of wallabies around. Great thing about this was, one of the reasons Simon invited me out there was because, well, mostly he needed somebody to type stop and start every so often when he was asleep. And also because he knew that straight after this observing trip was my 30th birthday. So we had a few days in Sydney afterwards, so I managed to have my 30th birthday in Sydney thanks to Simon. So going observing is not as much fun as it often seems. I mean, it's exciting and it's interesting, and you get to go places that normally you'd never go. And you get to take all this interesting science, but it's not quite this sort of delight, and especially if, like Simon, you hate flying, not a great thing. So how do you do science? The scientists are laughing. What we pretend, and in particular when we're writing up our science, and so we're writing a scientific paper, and we always sort of pretend that from the outset we knew what we were doing. So the view of how science is done is that you have a brilliant idea, and then you go out there and you test your brilliant idea. You write your telescope proposal going, I have a brilliant idea, and somebody goes, oh, you do? Have some time on a telescope. And you take that, and you go, oh, yes. And then at the end of it, you go, see how clever I am. Yeah, we're all brilliant. Doesn't often work like that. One bit that I think we're all very lucky is we can do the bit where we can do science where we get to choose who we work with. A lot of bits of science are done in huge collaborations where sort of you're forced to work with loads of other people. We've always thought extremely lucky in doing this, than doing a bit of science where we get to choose who we can work with. And this is sort of why we're all here today, and had the meeting earlier, is because we got to work with Simon and each other, and it was fun. And it made the whole process a lot more exciting. And we carried on working with him and working with each other because it's fun and it's enjoyable. But it certainly didn't work like that. Well, say it doesn't. Occasionally, about twice in my career, I think I can go, I had a brilliant idea, tested brilliant idea, and then went, oh yeah, it was brilliant. Most of the time, what you do is sort of look at stuff, talk about it a lot. You try and spot something nobody else has noticed. It's remarkable how much good science is done where you read something that somebody's done and you just go, oh, that's so obvious. Why didn't I spot that? Why didn't I think of that? That was something Simon was very good at, was able to just look at something and go, that thing, that's interesting, isn't it? And then he'd tell you about it and you go, yeah, that is interesting. Well, we should do something about that. Blind luck comes in a lot. Just happening on the right thing. It's when you go through a lot of Nobel Prizes. A lot of physics, especially the astronomy Nobel Prizes, are the Nobel Prize for blind luck. It's being in the right place at the right time. And along the way, there's a lot of trial and error and a lot of making mistakes. Now, as I'm always telling students, making mistakes is really important because you learn from it a lot. Now, usually what you learn from making mistakes is, I was an idiot, don't do that again. sometimes making those mistakes is sort of what helps you understand what's going on. And what you really, really want to do is work with people who are good at these things and understand this. There's an awful lot of bouncing ideas off each other. And in particular, working with Simon, a lot of that bouncing ideas off each other was done in the pub. And it really was science we were doing in the pub. Looking at Laura here, it is an amazingly useful place to do science because it's a place where you can throw out stupid ideas at each other. And 9 out of 10 of your ideas will get shot down as being stupid. But 1 in 10 will be sort of, yeah, you know what, that might have some legs. So there's a lot of trial and error and mistake making that goes on. And that, to my mind, and Simon certainly felt this as well, and we talked about this, is that's part of the fun of doing it, is that making mistakes and things coming up. One thing Simon did, it's come up a few times today, basically the entire, half the afternoon was talking about, wish I'd use Simon's sparkling jewel box, as Ignacio called it, rather than just Simon's cluster, which is a bit boring in comparison. But it's a cluster WD1, Westerland 1, which to all of us is something which sort of, we always think of this as Simon's. This was something that was spotted in the 1960s. And if you sort of squint, I've dug out the original paper for the first time ever the other day. Sort of squint, and there's sort of something there. There's something. This was spotted in the early 60s by Westerland, and it was the first one he spotted, so he called it number 1. Then it was pretty much ignored for about 40 years. And Simon looked at this, and we were talking earlier about why it was. There was an interesting object which happened to be here, which caught his attention. And I remember having a conversation with him where he was going, you know what, I think this is really interesting. Because one of the problems you have in doing astronomy, especially astronomy within our galaxy, is what we call extinction and reddening, which is basically there's a lot of stuff in the galaxy. There's a lot of gas and there's a lot of dust, which are these tiny little particles which get in the way of the light that's coming to you. And this effect is the reason I picked this picture is why sunsets are pretty. Because we see this effect of stuff getting in your way, in particular little bits of dust, when the sun sets. Because when the sun is in the sky, you sort of high up, you don't look at it. It's a really bad idea to look at it because it's really, really bright. Only people like Donald Trump look at the sun unprotected. As it goes down towards the horizon, you can look at it. And round about sunset, you get these beautiful views where you can look directly at the sun. The sun at this point looks a lot redder. What you're doing at this point is you're looking through a lot more of the atmosphere. As it's down towards the horizon, you're looking through more of the atmosphere. And so the light coming from the sun, quite a lot of that gets scattered. The blue light in particular gets scattered, so the sun becomes less bright and it becomes more red. And this happens in the galaxy a lot. And the more of this stuff you've got in between where we are on the Earth looking at things and the thing you're looking at, things will look fainter and fainter and redder and redder and redder to the point at which sometimes if you're looking in the visible light that we can see, you don't see them at all. And Simon basically went, there's a lot of dust and gas in between us and this, and yet we still see some stuff. So the stuff we see must be really, really bright. If it's really, really, really bright, then it's a really unusual sort of type of massive star. And we're only seeing the tip, very, very tip of the iceberg. And that there must be loads more things there, because these are very rare. So if we're seeing some really, really rare stuff, there must be loads of other stuff there. So sort of, we should go and look at this. And so we did. And the volume of work on this region, this is what we now see in it. there's sometimes when you're doing science where you remember something. Very often it's just sort of stuff happens and afterwards you go, I'm not sure what order stuff happened in. This I remember very, very clearly. That Simon was doing a lot of analysis of sort of what we were finding in this cluster. And my job was basically, he was going to tell me what was there. I was going to run it through a little computer program to go, this is how massive this cluster is. So I got an email from him going, here you go. It's, I can't remember, 150 stars, more massive than sort of 40 solar masses. So I was sort of, okay, type that into my computer program. A few seconds later, and chunk, threw out a mass of how heavy this thing was. I looked at the number and I went, well, that can't be right. So I emailed him and went, are you sure you're right? I got an email back from him going, oh no, there's more. I said, okay. And turns out, this is by far the biggest star cluster in the galaxy. This thing's got about 100,000 stars in it, in a volume of a few cubic light years. So a light year, it's about 3 light years between us and the nearest star. So it's take about that sort of distance and put 100,000 stars in it. And that's what this thing is. And it's incredibly young. Well, we can argue the toss about exactly how young, probably about 5-ish million years, which in astronomy terms is incredibly young. It's full of these incredibly massive stars in all sorts of weird states, doing all sorts of strange things, and we really don't fully understand it. And it's how this discovery of this came about. We talked about this. We sent this to Nature because we thought, oh, biggest cluster in the galaxy. That's got to get into Nature. No, they didn't. Well, the referees didn't like it, and as has been said today, I think they were probably annoyed that Simon found it and not them, so they wanted to downgrade its importance. But there's a huge literature out there on this object now, which I think all of us think of as sort of being Simon's cluster. So, probably about perfect timing. Massive stars are fascinating. There's a reason that all of us and Simon was so interested in them. It's because we don't really understand them, but we do know they're incredibly important, and that they're the origin of most of the elements that make the Earth and us up. They control how the galaxy evolves. And so understanding them is really crucial and really interesting that we don't fully understand them. And it was wonderful to be working with Simon on this for so many years. And as all of us have been saying today about how much we miss working with somebody who was just so fun to work with. And he was a really, really, really good scientist. He was really insightful. And he was also incredibly good fun with it as well. And lots of the truly crucial parts of doing science, of spending a lot of time in the pub, just bashing out the ideas. And I actually heard a story earlier, which I'd not heard before, about the time Simon lost his entire laptop by trying to write a telescope proposal in the pub and then spilling his beer on it and destroying it, which I'd never heard before, but it was sort of, oh yeah, I can quite believe that. So I hope I've sort of given you sort of an insight into why it is we're so interested in these things, and also partly how science works in the actual practical bit of doing it, which is sometimes incredibly frustrating, but depending on who you're doing it with, just can be such fun. And when you get places, to have other people as excited and as enthusiastic as you are by what you're doing is fantastic. So, thank you.
Thank you very much, Simon, for that excellent talk, giving us a real flavour of how you and Simon worked together and the fun you had along the way. Simon has offered to take any questions, if there are any. My colleagues have got a couple of microphones, so if you do have a question, wait for them to get to you so that the people who are online can hear what you say as well. So
You can get really technical. We've got a lot of experts down here.
Yes, one there. Well, two there, in fact. So, David, take them.
Yeah, so you talked about the ELT a bit earlier, so I wondered if you could say anything much about what the ELT will do for massive star science in general, some examples or ideas?
Yeah, I mean, the point of building something that's 40 metres across, so, I mean, this is 6 billion euros, so it's a lot of money into this, is it's largely, the bigger the telescope is, the more light you can collect. And so you can look at fainter things and you can look at things a lot faster. So one of the things that's really, really going to help with massive stars is when they are distant or when they're behind a lot of this dust and gas. So they're very intrinsically bright, but as far as we're concerned, they're really quite faint. Is there's stuff we really can't get at the moment, and it allows us to get at stuff that we can't get at the moment, see things that are much fainter. It will also allow us to do things a lot faster. So when you're trying to get information, you want to collect light, and ideally enough light that you can spread it out into all the different wavelengths and get a spectrum of light, which means you've got to collect a lot of light. And so when I went to the VLT, so this was an 8-meter telescope, and it was quite boring because we were trying to do a spectrum of some of these stars, actually in Western 1. So we'd point the telescope at it, and then I'd sit there for about 6 hours as it just collected light. Then I'd quickly look at it and then decide whether we needed to look at it for another 2 hours or not. I spent a lot of money on eBay and Amazon because there was really very little to do. You build something much bigger and it's able to do something like that in 10 minutes. So you're able to do stuff a lot faster. You're able to look at things you can't look at otherwise. And that's sort of massive stars. And the great thing about a telescope is you don't just use it for massive stars. You can use it for galaxies, for low mass stars, for planet hunting. You can look at atmospheres of exoplanets. So any bit of astronomy you're interested in, everybody is getting excited by the extremely large telescope. So it's just, wow, this is going to do so much.
Another question there.
Yeah, with our satellites, I've seen online that people are complaining they can't see the night sky very well because of them. And in particular, Elon Musk seems to be building more and more. Would it be a problem with the VLTs or indeed the ELTs in future?
Yes. Yeah. The crowding of space, and in particular, Elon Musk has got this sort of Starlink clusters. So these are small, very cheap satellites. And his idea is to sort of completely cover the world in these so that you could get internet access wherever you are on the Earth via these satellites. But there's so many of them. They are already causing problems in observations. They are a big, big problem. And being Elon Musk, he's making out that this is to provide internet access to poor, remote communities. Actually, it's much more likely so that he can flog internet access to people in their cars via this. It's as an astronomer, it's difficult to be particularly sort of neutral about this because it's going to muck up the skies. And the amount of stuff in space is becoming a big problem. I mean, even beyond sort of what it's doing to our ability to observe the night sky, it's putting more junk in space. It is a huge problem of how much junk there is in low Earth orbit. And every so often, bits of these junk hit satellites and take satellites out. And there's all sorts of stuff floating around up there. old satellites, defunct satellites, stuff that people have dropped when they're on, sort of you let go of a sort of tour, doing a spacewalk, that just floats around. So it's becoming a big problem that in particular low Earth orbit is getting full of space junk. And it is a problem we are going to have to address at some point soon. There's too much stuff up there. We need to work out some way of getting it down. People have actually come up with plans of this. You put big space nets up, just sort of go around and collect it all. But yes, and he's just adding to the problem.
Any other questions? Sally? Yes, and then one behind. Yeah.
I'm pleased there's someone after me. I am not an astronomer. This is going to be a dim question. Apologies. I'm on the logic that you went through with Simon's cluster, and it must be a huge cluster because there's lots of massive stars. So there's an assumption there that a cluster has the same number of massive stars per massive unit of volume, if you like. Is that?
You didn't referee our Nature paper, did you?
Shucks, you found me out. I don't think a physics education researcher would do that, but it's a nice try.
Yeah, there is, and it was not a dumb question at all, that there is an assumption that sort of when you get massive stars, you get a lot of low mass stars as well. Now, when we look around, that assumption always seems to be true. There's a few weird cases where we go, oh, we've seen a massive star, but there don't seem to be a lot of low mass stars. I wonder why that is. But almost always when you've got a massive star, you've got loads of low mass stars there as well. It would be a really, really, really weird thing. But actually, one of the complaints one of the referees had was sort of, oh, what if there are no low mass stars? To which the obvious response is, well, that makes it even more interesting.
You took us through a rough life cycle of a massive star, but you've said they're rather more complicated. I wonder if you could give us an example of a complication?
Oh, yeah. Well, one of the big complications that we've been talking about quite a lot today is you don't tend to get one massive star on its own. You tend to get two massive stars together. And actually, they tend to be really quite close to each other. Close enough that actually they start interacting with each other. So you can get all sorts of weird stuff happening where you've got two massive stars, and to begin with, they're sort of separate things, but then they start evolving. And when they evolve, they tend to get bigger. And then they start interacting. So what you can have is one of them giving material to the other one. So the thing that starts off the biggest can then give a load of material to the smaller one, which then ends up being the biggest. So there's loads of weird objects we see where we go, hang on, things are working the wrong way round. And the only way we can really explain this is that two stars are busy swapping mass between each other. And that makes things horribly complicated. And then you often have material around these stars as well. So you can have one companion star that comes in and messes up the material around it. And then if you've got one of the massive stars can evolve into a black hole or a neutron star, then that can start sucking material off one star, and then you get things called X-ray binaries, where you're sucking material off, it's falling onto the neutron star or black hole, it's giving out loads of... And so as soon as you get more than one star, that makes things much more complicated. Different stars can lose mass in different ways. So as they evolve, some of them shed their outer layers, some don't. And some shed them down to different levels, and then they can grow and they can shrink. And we really don't understand it very well. And it in particular is, I had one for today. Everyone used to ignore the fact that you get these things in pairs. And now it's become clear you cannot ignore that because they basically are all in pairs. It's just how close they are makes a difference to what they do. One thing we ignored for quite a long time is the fact that these things actually rotate. We ignored that because it's difficult. And when you're doing computer models, which is I don't do computer models, this sort of thing, but I know from when you're building computer models, it's nasty enough. And then some observer comes along and goes, you do know those things rotate, don't you? And you go, yes, I know. I says, but that's really difficult. So you do one, and then you need a bigger computer to then go, actually, they spin. Actually, they spin really quickly. And there's all this stuff going on inside. And yeah, they're nasty.
There was another question here, I think. Yeah.
Hi, I just wanted to say thank you, because I'm not a scientist at all, and I'm a social scientist, but I really have understood more or less everything you said, so that's great. I just wondered, there's a couple of friends who wanted to come today who couldn't make it. Are you going to be putting this talk on the intranet?
Yeah, it's been recorded, all being well, and we'll put it on probably the School of Physical Sciences YouTube channel when we get it
Thank you.
there. Yeah. Over this side, yes.
It does sound all rather complicated. How do you see AI featuring in the future, making it less complicated?
Yes and no. There is a lot of fuss about AI. It's been around a while, actually, in science. And we used to call it machine learning. And generally, we still call it machine learning because AI has got a bad name. One of the big problems we've got is you can take huge amounts of data and then you're really not sure what to do with it. And up until fairly recently, you deal with this by hand. So you've got a person looking at this, and we've heard lots of complaints today about quite how nasty and complicated doing this by hand is. That, particularly that Simon, there's a quote from an email from Simon going, oh, this would be quick and easy. How many years was it? 7 or 10. And the trouble is that a lot of stuff is very, very complicated and really needs a human brain to look at it and sense check it. But in a lot of what we're doing now, we're just getting so much data, it's not possible for humans to look at it all. So there's two solutions there, potentially. One is sort of the technological solution of let's get computers to do this for us, which is the route most people seem to be going down. And then there's as somebody who works with computers, that possibly makes me more cynical about how good they are about doing things, is maybe we're getting too much data, and maybe we should slow down and spend more time understanding it. I'm getting some grins and nods there, because there's a lot of suspicion amongst scientists, I think, of some people are completely sold by this. And there's some things actually machine learning is extremely good at doing. There's a lot of stuff machine learning is very bad at doing. And a lot of people are getting really rather overexcited, I think, by what it is that computers are able to do. I mean, a lot of the fuss at the moment about those sort of large language models like ChatGPT and things like that, they're not very good. They can fool you into thinking they're good, but once you actually look into them, they're not that good. So I am somewhat suspicious at how much stuff they can do.
Well, I need to complement that because I'm actually working with machine learning here at the Open University in astronomy. It's a tool, I would say. It's helping us quite a lot, like thinking of a doctor who's trying to treat a patient with cancer and trying to diagnose cancer properly. He's looking at a lot of images from MRT or that kind of imaging devices. That's the same thing we're doing, especially when we're coming into area of space-based telescope like the new Euclid mission, where we have billions of images of galaxies. You can't really crunch through. Well, that's a point where you could say probably too much data. Or at least the only chance we've got nowadays, crunching through the data and getting some information through that, is with the help of computers. And that's why it's almost computer vision, image recognition, object detection within those images. So it's not really what you expect general artificial intelligence would be. But it's at least a tool that helps us quite a lot at the moment.
Yeah, I mean, complementing that, one thing it is very good at is that there's lots of surveys being done at the moment. In Sheffield, we're involved in various of these. We're looking for transients. So this is, you look at the sky and you look for stuff that changes. This could be supernovae or various other interesting things that massive stars and all sorts of other stars do, is they can suddenly change. And you do want some automated thing that is, as the data is coming in, it's looking at it and it goes, ooh, something weird, and sends out an automatic flag so that other people can, and then that can only be done by computers. So computers used to flag things for humans to look at is brilliant. I think what I was talking about was something sort of slightly different, is where you just throw data in one end of a computer and then totally believe the stuff that comes out the other end and write a paper going, oh yeah, well, the computer says.
Any more questions for Simon? One there.
Hi, you had a really nice slide earlier on of like a cross-section of a massive star that had an iron core and different shells coming out. How do you know how the makeup of that star exists?
That's a very good question. It's partly theory. So we see what they look like and how they evolve. And we can mix. So what's going on with sort of the fusion reactions is that's nuclear physics, which we understand reasonably well. And we can look at things like the sun, and sort of because it's so close, we can get a lot of information out of the sun about how it's going through fusion. And so we can go, well, know how that's working. We can do experiments in nuclear reactors and things like that to understand the nuclear physics. So we think we know how fusion works. And then you can build a model that goes, oh, okay, this is what we think one of these massive stars should do. And as it goes through each of these steps, this is the next thing that should happen. And so that leads you to this sort of, okay, in these places it's hot enough to fuse up to these levels, these places hot enough to fuse up to the others. Now, that, if it was just that, you wouldn't fully trust it. But then what we can do is go, well, if this is indeed what happens, we can make predictions as to when these things go supernovae, what elements we should see when they go supernovae, and compare those to what our models tell us should be there, and we go, yeah, that's not bad, that's fairly close. And we can also go, well, if we look at the distribution of different elements in the galaxy, particularly if you look at something like the sun, you can go, well, how much hydrogen is there, how much helium is there, how much of each of the other elements are there? And we can go, well, if we've got a model where massive stars are working through things and they're building up the elements and then they're releasing them, what would we expect this distribution to look like? And it's sort of like we see it. So various bits of evidence come together, mixed with theories, and in particular theories about nuclear physics, which you can test in the lab as to sort of, okay, this is what it should do. And it brings us together to a picture where we go, it's probably something like that. And the details we are not getting right. A lot of the fiddly details we know we're not getting right, but the general overall picture fits everything we see and everything fits together nicely. But that's always a good question to ask of anything in astronomy is, yeah, you've shown us, how do we know it's like that? It's sort of, a bit of guesswork.
Anybody else? Oh, one more, yeah.
I'll never forgive myself if I don't do this. Simon's birthday was the 10th of March. What star sign was Simon?
Oh. I don't know.
He's a Pisces, I believe. He was.
So
He really loved it when he introduced himself as an astronomer and someone asked him about star signs, one of his favourite things.
we all do, yeah.
It happens less often now, thankfully.
Okay, well, I think on that note, thank you all for coming. Let's thank Simon again.